Now, in this video, we are going to take up one more problem on the stress-strain relations. The problem number 11. The following data pertains to a tension test conducted in the laboratory. The data are: the diameter of specimen is 25 mm, gauge length of specimen is 200 mm, extension under a load of 20 kN is 0.04 mm, loaded yield point is 150 kN, maximum load is 225 kN, and the breaking load or loaded failure is 120 kN. So the length of the specimen after failure is 275 mm. Net diameter is 18.25 mm. So determine: one is the Young's modulus, then second one is yield stress, third one is the ultimate stress, and the fourth one is breaking stress, fifth one is percentage elongation, sixth one is percentage reduction in area, and number 7, safe stress adopting a factor of safety of 2.5. So as we know that what is the Young's modulus? To find the Young's modulus, calculate the value of stress and strain within the proportionality limit. So what is the proportionality limit? For the load of 20 kN, an extension is given and the load is within the proportionality limit. So you take that Young's modulus, which is consider this as the load to calculate the Young's modulus. So here first we want to find out the stress value. What is stress? It is defined as P by A. What is the load at the proportional limit is 20 into 10 to the power of 3 divided by pi by 4 into the cross-sectional area of the specimen, which is 25 square. So on simplification, you will go to get it as what is 0.744 Newton per mm square. Similarly, what is strain? Strain is nothing but delta L by L. So what is the extension within the proportional limit of the, which is 0.04 mm divided by original length of, or the gauge length, which is going to be 200. So on simplification, you will go to get it as 2 into 10 to the power of minus 4. So we need to find the Young's modulus. Since we know the value of stress and strain, we will go to get the Young's modulus, which is sigma by epsilon. Sigma, you substitute the value of sigma as 40.744 divided by 2 into 10 to the power of minus 4, which is the epsilon value. On simplification, you will go to get it as 203,720 Newton per mm square, which is 203.72 into 10 to the power of 3 Newton per mm square. Then Young's modulus will be equal to 203.72 kilonewton per mm square. So now we are going to take up the yield stress. What is yield stress? The load at yield point divided by the original cross-sectional area of the specimen. What is the load at yield point, which is 150 into 10 to the power of 3 divided by the original cross-sectional area? Since it is the diameter is 25 square, so diameter is 25, therefore pi by 4 into 25 square. On simplification, you will go to get it as 305.6 Newton per mm square. So when you are taking the ultimate stress, what is the ultimate stress? That is the maximum load divided by the original cross-sectional area of the specimen. So what is the maximum load you will go to get? It is 225 kilonewton. So that is 225 into 10 to the power of 3 Newton divided by pi by 4 into original cross-sectional area. The diameter is 25. That is pi by 4 into 25 square. So which will be equal to, on simplification, you will get it as 458.4 Newton per mm square. So the next one, we will going to take up the breaking stress. What is the breaking stress? That is the breaking load or the loaded failure divided by the original cross-sectional area. So what is the breaking load? 120 kilonewton. So that is 120 into 10 to the power of 3 divided by the original cross-sectional area, which is pi by 4 into 25 square. So on simplification, you will going to get it as 244.5 Newton per mm square. So what is true breaking stress? Which is the breaking load or loaded failure divided by the actual cross-sectional area of the specimen. So what is the breaking load? Again, you take pi by 120 into 10 to the power of 3 divided by the actual cross-sectional area, that is pi by 4 into 18.25 square. So that will be equal to, on simplification, you will go to get it as 458.74 Newton per mm square. So then we will going to find out what is the percentage elongation. See, the percentage elongation is the total increase in length divided by the original length into 100, which is in the percentage So what is the total increase in length? 275 minus 200 divided by 200 into 100. So on simplification, you are going to get it as 37.5%. So now the percentage reduction in area. So original cross-sectional area minus final cross-sectional area divided by the original cross-sectional area into 100. So what is that? It will be, you have the original diameter as 25 and the final diameter as 18.25. That is the diameter of the failure. So that is pi by 4 into 25 square minus pi by 4 into 18.25 square divided by pi by 4 into 25 square into 100. So then we are going to get it as 46.7%. So what is the safe stress, which is the yield stress by factor of safety? Yield stress is 305.6 divided by work factor of safety is 2.5. So on simplification, you will going to get that value as 122.24 Newton per mm square. So this is how you will be able to find the solution for the last problem. Now we are going to take up one more problem here. It's something similar to the same which has been done for the previous problem. Which as the tensile test was conducted on a mild steel bar, the following data was obtained from the test. So that is the diameter of the steel bar is 16 mm, gauge length of the bar is 80 mm, the loaded proportionality limit is 72 kilonewton, the extension at a load of 60 kilonewton is 0.115, loaded failure equals 80 kilonewton, final gauge length of the bar is 104 mm, the diameter of the rod at failure equals 12 mm. So determine the Young's modulus, then proportionality limit, true breaking stress, and the percentage elongation. So to do that, so first what is the Young's modulus? So to find the Young's modulus, calculate the value of stress and strain within the proportional limit. So that is the condition for the Hooke's law. The loaded proportional limit is given, but the extension corresponding to this load is not given. So the loaded proportional limit is given, but the extension corresponding to this is not given. But what he has given, since for the load of 60 kilonewton, which is within the proportional limit, the extension is given. So the extension at the 60 kilonewton within the proportional limit is given. So the stress at that or the load at that proportional limit also has to be considered. So we have to consider the 60 kilonewton load. So what is stress, which is P by area? P is 60 into 10 to the power of 3 divided by pi by 4 into 16 square, which is since the diameter of the bar, since it is the round bar, so naturally the area of the circle, which is pi by 4 into 16 square. So on simplification, you will get the value as 298.4155 Newton per mm square. So what is strain? Strain is nothing but delta L by L. So delta L is 0.115 divided by 80 mm. So on simplification, you will get that value strain as 1.4375 into 10 to the power of minus 3. So since we need to find out the stress, the Young's modulus within the proportional limit, E will be equal to stress by strain, which is substitute the value of stress and strain here, 298.4155 divided by 1.4375 into 10 to the power of minus 3. On simplification, you will get that value as 207,593.4 Newton per mm square. So in the second case, the second one which you need to find out is the proportionality limit. So loaded proportionality limit divided by the original cross-sectional area of the specimen. What is the loaded proportionality limit? Which is 72 into 10 to the power of 3 divided by pi by 4 into 16 square. So on simplification, you will get that value as 358.1 Newton per mm square. Similarly, we are going to take up the true breaking stress, which is loaded failure divided by the actual cross-sectional area in the specimen of the bar. So here the loaded failure is 80 into 10 to the power of 3 divided by actual cross-sectional area at failure, which is pi by 4 into 12 square. So on simplification, you will get that value as 707.3553 Newton per mm square. Similarly, the percentage elongation is the total increase in length by the original length into 100, which is final length minus the original length by original length. That is 104 minus 80 by 80 into 100. So it will be expressed in percentage, which is 30%. Similarly, so this is how you will be able to solve this particular problem. Thank you.